We are in discussion for orthogonal components. Orthogonal components can exist or independent components. So it's pretty simple. Means if I have a class, then class is known by its attributes. So class is represented through its attributes. Otherwise, class that is also called an abstraction data means it is not a data. Okay, inside it there are attributes. Now, like for any data type, the attribute can be id, type, and value. So the biggest challenge is that how we find the attributes those are independent to each. If I have a class A and it has attribute a1, a2, and a3, then a1, a2, a3 or up to an, then a1 to an should be independent to each other, or in other terms, or in angular dimension. Okay, so in angular geometry, where we see things in radians, then it should be orthogonal to each other. If it is orthogonal to each other, then the energy means then the energy or the shadow of one component would not fall on other. If that is true, then the final value what an object contain would be kind of some summation of the attribute. It would be maximum. So minimum storage of minimum storage required, and maximum the kind of strength that we get. So that is orthogonal components. Like a vector is a class. If vector is a class, then it has three orthogonal components. So that is along x direction, y direction, and z direction. So we are talking about a science where the abstraction, the data abstraction like class should be represented through orthogonal component, independent variable, independent component. Then when we do any mathematics on the class, then finally it will lead to doing the mathematics through independent variable. So if I have a class and it has three components with the class, three components are attached. Now, if I want to do any computation, if I want to do any computation on class, so if I want to do any computation on the class, then computation of the class, the mathematics that we want to do on the class, that would be delegated to the component. So component would take the full load. That is the idea. Like if I am building a house, then if it is not a pillar house, okay, so if there is a house, there is a house and it is made up of bricks. Okay, so all the side there are bricks, then full load of the roof will fall on bricks. If there are 1000 bricks, then full load will come on 1000 bricks. Okay, now we have to think about 1000 bricks. Now there is a roof, and under the roof four walls are there, and each wall is made up of bricks. Now at the four corner I put four pillars. Okay, like this is the roof of the building. Now at the four corner I put four pillars. If I put four pillars, then now I can remove the bricks. That is the idea. Now, if I remove all the bricks, all the side walls, then the roof would stand on four pillars or three pillars. This is class. So, if we don't think about orthogonal components, then number of attributes in the class would be infinite, and it would sit on all infinite attributes. It will be complex, and non-realist. But if we think about the pillars, the orthogonal component, the class would sit on the orthogonal component. If that is true, then the load of the class would fall upon few pillars, few orthogonal components. Then whatever the computation we are trying to achieve that we impart on the class, those computation load would come on the orthogonal component. So that is the concept. Now, orthogonal component should be invented, should be discovered, should be found out in a way that it will be independent to each other, and altogether the independent component or the orthogonal components would take the maximum load. That is the idea. Now, if vector is a class, then it has three independent components. In three orthogonal component, independent variable. One in x direction, one component, one in y direction, one in z direction. So if we see angular signs, okay, in angular domain or axial domain, then all three are 90 degree to each other. Now, if we want to do any computation over the class, then computation would happen, then class would delegate the computation on to the component. So final computation, achieving the final computation that would happen on vector class on its orthogonal component, that is the science that we are talking about. Now, we have seen that if I need to find dot product of two vectors, then the dot product is defined as if two vectors are parallel to each other. Okay, so if two vectors are parallel to each other, then dot product is multiplication of their magnitude. Okay, if they are parallel to, must be parallel to each other. So if they are at this angle, then we'll take out the cos theta, the parallel component only, and then whatever the parallel component comes, that is b cos theta into a. Cross product of two vectors is if two vectors are orthogonal to each other. If two vectors are orthogonal to each other, then cross product is multiplication of their magnitude. If they are not orthogonal to each other, there is an angle between them, then we will find the orthogonal component. There are two components of any vector. One is, okay, one is we can say in direction. So in direction component or horizontal component, or another is orthogonal or vertical component. Two component. One is this is b, then b cos theta. Another is b sin theta. Now, if I get b sin theta, that is the orthogonal component of this vector. So b sin theta into a is the cross product. What is the cross product? Brings a area, because since these are orthogonal to each other, it brings an area. Okay, since they are orthogonal to each other, then there is a surface that touches the two vectors. That is the concept. So if this vector and this vector, if we draw a plane that would pass through these two vectors, then that is the surface of the plane. So right now it is rectangle, but if it is like this, then I have to draw this, then it will be a parallelogram. So whatever the surface comes, the normal to the surface is the direction of the cross product. So it can be in two directions. So if I say, suppose that this is y-axis, the horizontal is y-axis, this is x-axis, and this is y-axis. So horizontal plane is xy plane. So cross product of x and y is whatever comes in magnitude, and then it will be in direct. So if this is the plane, then vertical direction is this. This is the direction of the cross product. If this is a and this is b, if I say I want cross product of b and a, then this is a plane. Now this is a plane called bx plane. y-x plane. Earlier, we wanted xy, x cross y. Now I want a cross b. Now I want b cross a. Then this plane is y-x plane because b is in y. If it is in y-x plane, then this is y-x plane surface normal vector. Okay, that is the direction of the cross product. So rather than, so what, this is what we saw. So there are three ways we calculate the cross product. One is, if I have vectors like this, then if this is theta, then b sine theta is the component, is this the kind of its vertical essence of this component, and then v b sine theta, certainly it would not be that much. Whatever we see now here, okay, if I draw a parallel line, whatever the height we see, okay, so it will come up to here. So that is b sine theta. So whatever rectangle it is making, b sine theta into a is the cross product or the area of the rectangle. Or if we talk in parallelogram, then the height of the parallelogram and base, same thing, b sine theta into a. That is the magnitude of the cross product. So this is one thing we saw. Another thing we saw, that if I have a vector b and vector b, so there is another vector called alpha I. So alpha I cross vector b. If that is the case, then vector b has three components. Now, what we talk now, sine theta, that is through vector multiplication. Now we'll come to component base. So there is a vector called alpha I. So it has one component in x direction, that is alpha. Whereas there is another vector called b. It has three components, b1, b2, b3 in three directions. Now if I want alpha I cross b, alpha I cross b1, b2, b3, these are the three components. So whatever the vector will get at the end, cross product, it will have three components. So first component is alpha into b's. Now, if you want cross product of two vectors, they must be orthogonal to each other. That is required. So alpha and b1. Alpha is the component, here b1 is the component. So what is the b1? b1 presents in orthogonal to alpha. Alpha is in x direction, b1 is in x direction. What is b1's component? v1's, we can say its part along y direction and z direction. That is the orthogonal to x. There is no part because b1 is completely along x direction. So alpha and b1 we cannot do cross product because they are in same direction. We want orthogonal direction of b1. So there is no orthogonal to b1. b1 purely in x axis. If it is purely in axis, there is no presence of this vector b1 along y axis and z axis. If that is true, then alpha into b1, that is gone. Now alpha I into b2j. So they are orthogonal to each other, I and j. So cross product will happen. So alpha into b2 and the cross product will be in direction of k. This is what we saw. Now alpha into b3 k. So b3 is in direction of k. So alpha in direction of y. So it will happen. Now alpha into b3. So alpha I into k, I and k, then it will be minus j. So the net, the vector what we are getting through cross product has two components. One component is in minus y direction, that is alpha b3, and one is in plus k direction, that is alpha b2. So minus alpha b3 in y direction and alpha b2 in z direction. So these are the two components. There is no component in x-axis because alpha b1 we cannot cross it, and b1 has no presence orthogonally to x-axis. So now two components. If I want magnitude of the cross product, then alpha b1 minus alpha b2, sorry, minus alpha b3 whole square plus alpha b2 whole square, that will come as alpha b3 whole square plus alpha b2 whole square root. So that is the magnitude. Direction of the vector is whatever the alpha b3 in minus y direction and alpha b2 in z direction. Whatever comes as a position vector, that is the direction of the cross product. So this is what it is. So 1 minus alpha b3 is going towards minus y axis and alpha b2 is going toward positive z axis. If these two meet wherever they go, that is the direction of the cross product. So this is what we saw. Now alpha I, instead of alpha I cross b, I'll say alpha I beta gamma, alpha I beta j and gamma k is a vector cross b. Then similarly we have to find the complete vector and it will have 6 addition, 6 multiplication. So where 2 will come as one component. Now we can say that alpha I, beta j and gamma k is A. So what is A cross B? So this is the way we try to find the component based analysis. Now we'll go with professional cross product with mathematics. So A1 cross third method. A1 cross B. Sorry, A cross B. Then A1 has component A1 B1 and A1 A2 and A3. So A1 has component A1 A2 and A3, whereas B has component B1 B2 and B3. So A1I plus A2J plus A3K cross B1I, B2J and B3K. Okay. Now, if that is the case, then A1 cross B is A1I plus A2J plus A3K cross B1I plus B2J plus B3K. Now, one by one, we'll calculate the cross. So, A1I cross B1I is 0 because they are in same direction. Now, A1I cross B2J is A1 B2 in K direction. A1I cross B3K is B3K is minus or A1 B3 minus Y direction. Now A2J and B1I. So A2J and B1I is A2 B1 minus K direction. Okay. A2J B2J same direction, so 0. A2J and B3K. So A2 B3 and in I direction, X direction. Like that, A3 B1, A3 B2 and A3 B3 will be 0. So we can go with the pure mathematics to find out the cross product. So if I have a vector A cross vector B, then A has 3 component A1, A2, A3. B has 3 component B1, B2, B3. Now each component of A will cross with all 3 vectors. Now there is no B vector. It's a combination of 3 vectors. There is no A vector. It's a combination of 3 vectors. Each vector in A would cross with each vector in B. And finally they will decide the 3 components of the resultant vector. So whatever it comes, so this will tend to be like A1, it will tend to be A2 B3 minus A3 B2 in I direction. Okay, and A1 B3 minus A3 B1 in Y direction. And finally A1 B2 minus A2 B1 into Z direction. So this leads to a kind of a matrix where first row is ijk. This is what we write a1, a2, a3 and b1, b2, b3. Then for I we calculate the determinant. Okay, for I we calculate the determinant. So for I there is a bar, and then if for I direction we will have a2, b3 minus a3, b2. for j determinant, for k determinant. So three determinants we calculate and we get the same result what we. So this is the full idea of the cross product. If we want cross product of two vector, vector must be orthogonal to each other. And if they are orthogonal to each other, then we can multiply the magnitude. What is the direction of the vector? That is the direction, whatever the plane these two vectors lives in, sits in, normal to the plane. So that is the concept of that is the concept of cross product. Okay, now instead of going with the vector cross product, vector has orthogonal component. So we settled with the orthogonal component. Okay, no need to talk about the angle between them, not required. Because orthogonal components, they are orthogonal to each other. They are at 90 degree to each other. So it will happen that we can say this is a modern way, this is a digital way in a binary way. So binary way in a sense means orthogonal or independent variable. It is a kind of candidate of high research. Means how we can map into binary area. See the way we are discussing now. They can be mapped into binary area. If they can be mapped into binary area, then two orthogonal vector computation can either be 0 or 1. So nice it is. Means no need to have. So we can say that the class layer, the vector layer, whatever computation we are doing through cos theta and sin theta, that is continuous analog. And when it comes to orthogonal component computation, it is binary. Okay, digit based, either it will be 0 or 1. So nice. So now if we come to orthogonal component, then whatever dot product or cost product we are thinking in the abstraction level, at the class level, now we come to orthogonal, that is the concrete and real level. So that is the concept. Now for the example, okay, now if I have kind of, I would bring. Okay, now we talked about the lighting system. Okay, so this is a kind of a surface. Okay, there can be a vertical surface, I believe. Okay, now suppose that these two vectors, they are making a surface. These two vectors are not orthogonal to each other. So now I want to calculate that how much light, this is the light, okay, then how much light would fall if I place on the surface. So they constitute a surface, and the surface that it will lit, okay, the surface it will lit is the cross product of the twisted vector. So the area it will glow is the cross product of these two vectors. Now if they are orthogonal to each other, the area, the rectangle what it covers is high. If they are not orthogonal to each other, then the cross product, whatever the area it will cover, is less. If they are parallel to each other, then there is a straight line. So if I put like this, then there would not be any glow because it's a straight line. But as so, the cross product of two vectors are 0. Now the way they are making the area in between, okay, area in between. Now this area is maximum when they are orthogonal to each other. Now if I place the light, then the full rectangle would be lit. But if I make less, then less it will be. If it come to on the same line, then there is no lighting. So this is the importance of the cross product. This is one thing. Second thing is, suppose the area we are talking, though it is a circle, but the area what we are talking about, if this is the area, so one thing is how big the area is, that is the cross product. And what is the direction of the cross product? The cross product direction is the normal of this surface. So if two vectors are aligned in a way, the surface is not normal. Okay, so even though there is a torchlight, but we can see it's not falling. Now it is falling. Okay, so cross product has importance. See, gone. So in OpenGL, this is how we do the computation. So now there is no light. We can see easily, but okay, so there is no light. Now full light. Okay, so like this, there is a light, but if I rotate like this, there is no light. So first thing is that how big the surface is. So surface, how much the big is, that is the magnitude of cross product. So cross product magnitude is how big the surface is. So that is the concept. If surface is big, then it would receive the more light. Now, what is the direction of the surface? So two things we see in cross product. Magnitude of the cross product, that is how big the surface is, and direction of its normal vector. So, if the normal vector direction is in along the torchlight, that is the dot product we have described, then it will receive the maximum light. Like sun is coming from there, and suppose there are two vectors, and this is the area of the vector, then we can see the glow. But there is no glow now. See the glow. There is no glow now. Okay, so in this fashion, both things are coming into the picture. The cross product magnitude, that is the area of the surface, and cross product direction, the direction of the area. So area has a direction, right? Area, any area has a direction. Okay, same area, if it rotates, its direction is changing. So cross product has magnitude, that is the area, and a direction. So first magnitude talk about that how much light it should receive, because less area, less light. And second thing, what is the direction of the cross product? This is the cross product, the direction of the cross product. So that is how much light it would receive. That also matter on the direction of the cross product. So if fixed, light is fixed that it is coming from this direction, and there are two vectors in some plane, then if I calculate the cross product, the whatever we see in between, okay, in between, that is the surface. So surface should be maximum, so they should be orthogonal to each other. First thing, and whatever their plane, the plane what they make, that plane's normal should be aligned to the light source. If they are like this, then there won't be any light. Okay, if they are like this, then there won't be any light. But if they are like this, then there will be light. So this is cross product. Now other example for the cross product is if I have magnets. I really have magnets. Okay. So if I have two magnets, okay, this is one is north and one is south, one is positive and one is negative. So you can see, okay, it sticks. Now this is north pole, this is south pole of the magnet, positive and negative side. If I keep like this, it's attracting. So now there will be magnetic field from the north side to south side, okay, or positive side to negative side if they are near to each other. Okay, that magnetic field is decreasing now. It is very high. Just trust me, it is very high. See, okay, it is very high. Now less. I can feel the power. So now if I so when there is a kind of two pole of magnet, okay, positive and negative pole or north and south pole of a magnet, then if I place a wire, okay, so probably I'll show in future. So if I place a wire, okay, now there is a north and south pole of the magnet. Now there is a north and south pole of the magnet, and there is a wire in between it. So there is a wire in between it. Now if I flow electricity through this wire, okay, so magnetic field is in this direction, electricity is in this direction. They are orthogonal to each other. If they are orthogonal to each other, then it will it will create a force in the perpendicular to their direction on the wire. That is the concept of DC motor. Means if there is a under a magnetic field, so magnetic field has direction. Suppose this is x-axis and there is a wire in between, that is y direction. So there will be force that will come in the wire in z direction. Okay, so the direction is communicated as L cross B, where L is the wire direction cross B. So here the wire direction is Y. So Y cross X, that will come in minus Z direction. So if there is a magnetic field along X direction and there is a wire along Y direction, then Y cross length of the wire cross B, okay, that is the force that it will place on the wire down the line, so minus zx. So net force is bil. So B is the magnetic field and I is the current and L is the length of the wire. So that much force it would impart if they are orthogonal to it. Otherwise, we know very well how to calculate the orthogonal, either sine theta or we will go with component wise. So magnetic field will have three components and length will have three components. If a magnetic field is exactly in x direction, it has y and z component as 0. If the length of the wire exactly in y direction, then its x and z components are 0. Now we will calculate the L cross B. L cross B. Then in that case, we'll get the torque in minus negative Z direction. So net it will be current into length into magnetic field. That much force it would impart. So there is a like a DC motor. Now we can see there is a magnetic. This is a typical DC motor, and all around it there is a round magnet. There is a round magnet. Okay, if magnet is round, then magnetic field will be through its radius, and the wire we can see the wire. Okay, now this yellow color is the wire, and round is a stator. Stator means magnet is static. White color what we see is the magnet, and in between the yellow color is the wire. Now, wire is placed inside the magnet in a way that it will be perpendicular to the magnetic field. So, it will place a torque in a way or force, torque is angular force, in a way that it will start rotating. But idea is if I have a wire like this, this and this, suppose, and it is a magnetic field in this direction. So, magnetic field is in this direction and wire wire is like this and this and this. So if it is in wire is in this direction, the push will be down. Okay, okay, means current is in wire is in this direction, current in this direction. The current is then current will flow parallel to the magnetic field. So there is no torque. Then current will flow in negative y direction. Then torque will be up. So it will be like this. If it motor will rotate, then there is no torque. So if there is a wire in a rectangular fashion, this, and this, then this side wire will get torque down and this side wire will get torque up. So it will the motor will rotate like this. If it rotates, then this side wire is coming here and current is flowing in reverse direction. So it will rotate like this. So there won't be any rotation. So there will be a commutator, something like that, which will change the current direction when it rotates. So in this direction, when wire comes, the current will always flow in this direction. When whereas the other side current will always flow in there. When the coil moves and it comes like this, then still current will be flowing in direction because the commuter will change it. So this is how the DC motor rotates in the magnetic field. So I have already shown it. So this is DC motor, and this is kind of how it rotates. And then I'll place a battery and I'll see that if it really rotates. Okay, so I'll place a battery. See, I'll take out the battery. Okay, and so the current is going inside the battery, inside the motor, and inside the motor same coil and magnet is there, and as soon as current flows, then the magnetic field and electromagnetic field inside the wire, they are perpendicular to each other. When they are perpendicular to each other, then whatever the cross product comes, that L cross B, that much force it will impart. So it will start rotating. So this is the best example of, I would say, of the cross product. See, okay. So I'll try to show through this magnet later. So I'll make a current and in between the magnetic field, and the wire should start moving here and there. So that is the concept. So so that way, kind of we calculate we see the idea of cross product. So cross product makes sense when we get product of two vector through orthogonal way, whereas dot product makes sense when we calculate the product through, not through orthogonal way, through inline way. If two vectors are inline, in phase, in direction to each other, and then we calculate the product, that is dot product. Okay, but if two vectors are orthogonal to each other, then we calculate the product, then it is cross product. So cross product lead to area, where any surface area has a direction. Any surface area has a direction. So if two vectors are orthogonal to each other, it leads an area, where area has a direction. If two vectors are in same direction, there is no area. So dot product is also called a scalar product. Like if I am moving this torque along x-axis, then force what we apply, it should also be, this is the force. If I apply the force up, then there is no work done, because work done must happen along x-axis one. So if I apply force, it is going little bit. But if I apply force in direction of the mass that I need to move, then it is so fast. And it is just coming like, okay, or okay, but no, it is not moving. Little bit it is moving. If I make horizontal, full moving. So dot product makes sense when two vectors are in same direction, then their product of their magnitude. Cross product when they are orthogonal to each other. Okay, it is really hot here. I don't know this year how it will go. It is very hot somehow. Okay, so to beat the heat, we have a kind of banana. Okay, so we can have yummy. Sometimes it is nice that it is really hot.